Okay, can start.
Yes, let's start the thing. Yeah, okay.
Yeah. Okay. Right.
Okay, so today our speaker is Deniz Tahmouresi. 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 France. Yeah, from University of Tehran.
Yeah.
Okay, yeah.
Okay, I'm actually let me introduce myself. I'm a PhD student in University of Tehran, and I'm doing a visit here for about 5 months. And this is something that we worked on, and I'm going to start my presentation. Okay, and once again, hello everybody, and thank you for coming in today, and thank you for the opportunity to for me to giving this talk. I'm going to talk about the unification, and especially the research that I do the unification for weak classical modal logics. It's a joint work with Michelle and some other colleagues. The outline of my presentation is going to be that I'm going to present you the basic definition of unification if you haven't heard of it or if you don't know the uh, concept of unification, and then I'm going to introduce to the main problem that we researched on, and at the end I'm going to give the main result and some future works that can be done in the future maybe. And the basic definitions are going to be about the unification itself and what's the unifier means and something like that. Before I go to the next slide, the unification in a general point of view is like solving logical problems, such that, for example, imagine you have a formula and you want to find the variables to substitute variables such that those variables make the whole formula topology. That's something we have also in algebra. For example, when we have so many, we have equations and we want to solve the equations and find the problem, find the answers. That's something like that, but in logic. So that's the big picture of what unification means. And for example, let me give you an example. For example, we have maybe something like this, and we call this x and y as variables, and we want to give them some value, so make the A tautology. For example, we can say if x goes to top and also y goes to top, then there is a total. This is something we are looking for. And in the unification, we are looking for all such answers, and that's the whole idea of unification. But to be more precise, let's say that substitution theta is a function on propositions which commutes with all connectives. And given a proposition A, we say that substitution theta unifies it in a logic if it makes it tautology. So that's something we have. And given two different substitutions, we want to say we can say one of them is more general than the other. If there is some other substitution like lambda, which combination of it with the general one makes it equal to the less small one. That's something that we have. Another important concept in this area is the projectivity. And we say that some substitution is projective in a logic if with assuming A, we can have that theta x is equivalent to x itself, and then formula is projective if such a property happens in that, and it's important because projectivity can give us the answer to our questions, because when some formula is projective, then it has the most general unifier. So that's why it is important. We can assume that the answer is a single form. We have just one general answer, and that's something very useful to know about. Uh, as I said in the example and the thing that I said before about the algebra, we are looking for the set of all answers that we can have, that we call it complete set of unifiers for a formula. And the complete set of unifiers should have three properties: that every substitution or unifier in the complete set should unify the formula, and for any other unifier, we should have something in our complete set of unifier which is more general than that. And the two different members of the complete set of unifier must not be, actually, should not be comparable. And when when this complete set of unifier have only just one member, then we say that there is a most general unifier for it. And in a typical category of unification problems, we are looking for this complete set of unifiers. The idea is to solve this and find the cardinality of this complete set of unifiers. So the unification type, when we say that what is the unification type of it, is exactly, we are talking about this complete set of unifiers and its cardinality. For example, as I said before, when it is projective, then it means that unifiable, for a unifiable formula like A, there is a projective most general unifier. It is projective and also it is most general unifier. And we say it is unitary when the answer, as I told before, when it has the just one member and it is the most general unifier. And it is finitary when the cardinality of this set is finite, and infinitary when we can characterize the complete set of unifier, but the cardinality is infinite. And at the end, we say it is nullerary when there is a unifiable A, which does not have the complete set of unifiers. And the main application of unifications are that when we want to find the admissible rules of a logic, when the complete set of unifiers are definable and we can compute them, then the admissibility of inference rules become decidable, because you have a complete set of unifiers that you know what are they, and then for admissible rules you can apply every member of the complete set on the rules and see if, because on the rules, and see if they are if it is admissible or no. Because for something that I should must say is that when you have the complete set of unifiers, like for example this two, and you have a rule, applying it on the first part should result second part, and this is something you can use to say that if the admissible rule is decidable or no, and it is not applied to check the admissible rule only for the ones that in the complete set of unifiers, because they are the most general answers. So if you can apply them to those ones, that's enough. You don't need anything more. And if we want to have a literature review over the results that have been,
So,
yeah.
to check, so if some rule admissible, I guess you basically what? So you, okay, right, you have, for example, the finite unification time, and you look at all the unifiers, and then you simply look if like the result of corresponding substitution. So for the result of corresponding substitution, you have probable implication, right? So you can do this unify for the prem. Yeah. Sorry, wait.
And results if you did your literature review, but I want to give you some examples on some of the works that are more known. And for example, in the classical propositional logic, the unification type is projective and also unitary. I mean, the most general unifier has the property of projectivity, and it is the most general unifier. Also for the parametric one, we have the same result. But when we add some additional connectives like modals, modal operators to the logic,
So in the line 5, is it Emil erratic?
in the line 5,
In the line 5, yeah.
Minimal model project.
Is it yeah, sure, or is it yeah? No, no, above.
yeah,
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 yeah, sure. Yeah,
yeah, I have missed that. Yeah, exactly. And when we add the connectives to the uh, when we add the model connectives to our logic, like in model logic, then the unification type can change. For example, in S4 we have the finitary unification type. In K, we know it is nullary. And also, for example, in another logic which is called polymodal probability logic, it is also nullary. So this adding box also brings some axioms and rules which are can make the unification type a little bit complex than before. And also when uh, add, I can say, remove some uh, operators, or we can say that we add some restrictions to the logic. For example, in the implicative fragment of classical propositional logic, where we have just the implication. Also, the unification type, although that we know the classical propositional logic is unitary, the unification type changed to unitariness, especially with the parametric ones. Actually, that's something you have to note when we say parametric. We have variables and parameters are in most of the time all constants, and we don't have power over them. So that's what I mean by parametric. And when the axioms and the inference rules are weakened, for example, as in intuitionistic logic, then also the unification type can change. So coming from the classical logic, when you add or remove some restrictions, the unification type can be complicated. And the goal of our research was that to understand how weak modal systems behave under those some by adding the modal operator box. And it's some logic between actually classical logic and K, and we know K is nullary. So yeah, we want to see what is the unification type of the logic that we are going to introduce, that how it is going to react. So if you take the main problem is here that if you take the classical logic as a as the base form of it with all its axioms and everything, and add the model operator box, we want to know the unification type of it would become how, especially if we have a rule that we call weakness estimation that says if A and B are equivalent, then their box formulas are also equivalent. And the idea to solve this problem, especially at first, was that to map these box formulas to parameters. So it become like parametric classical propositional logic, and to solve the problem. But as we move forward, we saw that it is not so much straightforward, and it needs so many works to do. And One of the reasons and examples that you can see why it cannot be easily interpreted as parameters is that, for example, if we have some A like this and we have substitution theta x and the y, you can see that the box y is going to appear in this part and box x is going to appear in this one when you substitute them. And there's going to be some sort of circularity in the process because each time one box is going to add it inside another box and you're never going to stop somewhere. That's why it's not so easy to just interpret these boxes as parameters. This example shows that there is some sort of circularity in the process, and we need to remove this so we can have the unification type of CL box plus. I'm going to refer to this logic as CL box plus from now. Okay, so as I said, the idea is to use the classical parametric logic and also the CL box plus. But to start with, we are going to define our languages. L0 is the propositional language, as you know, with all its constants and the infinite set of parameters and variables and also all the connectives we have. And we say that L par is a restriction of that L0 to the just parameters and constant but. And L bar is a restriction of L0 again on the atoms but and ref. And finally, we are going to say L box is the L var with an extra connective that we said as before, extra connective box. And a general L substitution is something that we say that if I want to say it easier than something that I wrote, is that it is going to apply on variables and parameters, and it will commute with all connectives. And if the language has bots, then it is also going to commute over bots and will falsify its identity. That's something we have. And at the beginning, I talked about the substitutions in general in the unification context, and that was something that we here call L substitution. That is L substitution if it is general and also it doesn't change the parameters. That's something most of the time we have. It doesn't change the parameters are identity on. And also we say that we define an assignment. An assignment is also a function, but this time the assignment is identity on the variables. It, as before, computes with all connectives and everything, but it is going to change the parameters. That's something different between this one and the previous one. And also an assignment how is called correspondence. If it has these three properties that is going to change the parameters to some box we have in our language. And if two different parameters are equal, then they should be exactly the same. And also for every box formula, there is a P such that this equivalency is half. And from now, when we refer to tau in any other following the slide, most of the time we have the correspondence tau in mind. So these properties are going to happen unless otherwise we declare that it is not. Up now, actually, as I said before, we have seen an example which was have some sort of circularity in it that I told before. And to solve that, because we see that the box are going to appear every time that you substitute the theta in that in the formula. But to remove that sort of circularity, we need to add some sort of restriction over our uh, substitution identifiers, so we can make everything smoother and easier because we need some sort of restriction. And that's something is introduced in this slide, actually F unifier. And the F substitution is said that to be for every variable x and parameter p belong to the subformulas of theta x. That sub means the subset of subformulas of theta x. We have that p in the restriction function f. And F unifier then it is something that F substitution and also unifies the formula. And as before, we can also say something is F projective if it is F unifier and has the projectivity as well. And some interesting result here is that we can see that although in this context a formula can be F unitary, but it is not F projective, but it can be not projective. So the F unifiers are that we are going to see are unitary, but they are not projective. So this is not the case that every time we have the unitariness, we have also the projectivity. But if we have the projectivity, then we can have the unitariness. And this is an example with the following A's and the restriction function that allows only x to have p and y to have q. And what do we mean by this? That in theta that's going to substitute this formula and unifies it is not allowed to use q in the x in the theta x, and it is not allowed to use p in the theta y part. So yeah. And we showed that the F unification type of classical logic is either unitary or unitary. Moreover, this is the result that we have. Moreover, we have shown that it is exactly unitary. And to prove this, the idea is of using f-exacts. F-exact formulas are something that we say a formula actually is defined f-exact if there exists a F-unifier theta for it such that for every formula in the subformulas, in the language of subformulas of it, that unified by theta, it holds that A implies B. And actually, this means that A is the strongest formula among all the subformulas and I can say language over subformulas of A that is unified by F substitution. And also we have another main idea here to prove that one and that is X projection, that it says that if we have an X of atomic formula, X projective is when some substitution doesn't touch any variable in X, and A, according to A, theta is identical. Theta X is equals to X, the corresponding to X, and theta A is corresponds equivalent to B. For some, we only have variables in X. And this is the thing of X projection. With these two main ideas, we can prove that the unification type of classical logic is unitary. And this is the result that we have actually Mojtaba and his colleague has proved that the A is X projective for every A and X, and the X projection is unique and equally and actually is equal to the uniform cross interpolante of A. And this result also hold for classical logic and intuitionistic logic in the paper that they published. And Finally, for the restricted unification type, the main result that we are looking for is that in classical logic, every if exact formula is then F unitary with the definition of F exact and F unitary is that I told before. We are not going to use that F unifiers and F substitution and all the idea that we talked about to prove that to find the well-founded unifiers of classical logic. And what do we mean by well-founded is that for two parameters, that I said before, for two parameters, P is less than Q. If P's appear in subformulas of theta, tau, G, that's something we have in mind. And this relation should not be infinite. This relation should not be infinite because then, or have some sort of circularity in it. So that's something we are looking for as well. And substitution theta is well-founded unifier if it has also make a topology and also be well-founded. And here, once again, we use the assignment tau, and the substitution tau, and tau is an assignment, as we said before. We say that tau is theta is tau well-founded if the combination of those two are well-founded.
Could we go a bit back? So for this relation, E less than theta Q. So how would you define? So you say that what? So P is an element of what size?
Okay, P and Q are two parameters.
Okay, sure.
Yeah, and the P is less equal than based on according to theta.
Okay.
It's less than Q if it is in the subformulas. I think
Sure. But the subformula of what?
of the combination of theta, tau, Q.
So what is tau?
Tau is an assignment. I have to say before, but yeah, tau is an assignment. And assignment means that it can change the parameters. It works on parameters. That's why Q is a parameter. Tau works on that one, and then it changes, and the tau is going to move parameters to boxed formulas. That's something we had.
So arbitrary or fixed?
No, that's why we said tau well-founded, because it can be defined in any way. It depends to tau, but it is not something fixed that we take.
That relation depends both on theta and tau.
This one?
Yes.
Yeah, some sort of, yeah, exact, yeah, because
Okay.
yeah, tau is something that, as I said before, is going to change parameters to boxed formulas. You can keep that in mind, but that's easier to yeah. And first tau is going to change the Q into its parameter to its box formulas, and then theta is going to. And yeah, tau is not fixed, but the well-founded, it can be anything every time we are working with a specific formula, but the theta and tau is then combined to solve our problem. And also for a restriction function that we see before, then we can also say that P is less than Q, depending to tau and F as well. If and only if it is appearing in the subformulas of tau Q, or for some x, P belongs to Fx. And finally, we say that F is also tau well-founded if this relation is well-founded. There is no sending seven. And the tau well-founded unification part for classical logic is also unified. That is the result that we had. Every time we define a restriction or something, as I said at the beginning, then we have to calculate its unification part, because we need all this to address our main problem. And till now, actually, we have seen that the result that I gave you are in classical logic because there we use some parametric classical logic, actually something we have, and the results will belong to that part. Now we want to relate that classical logic, parametric classical logic, to the CL box. That's something we have to the box formulas. We need to relate these two parts. The result we have over there with this one that we are going to have in the box part. And to do that, we need one more definition that is called faithful, and then one result that I'm going to talk about. And the idea of that definition is that I'm going to give you the idea that we say some substitution is faithful if when it substitutes the amounts, the box formula that it is going to appear or belong to the formula itself. Actually, we said here to belong to the L box, but in more in future we can see that it is going to be something from the formula itself, and the idea is that there is nothing outside the formula that is going to appear in the proposition in the formula when substitute when using theta. It's going to some sub formula of the same formula, and that's something we need. And then we can relate these results together, something that we have the tau well-foundedness that we have in the classical logic with some faithfulness that we have in the L box and CL box plus. And this is the relation back and forth. These two are the back and forth typical thing that we have in most I can say things that it's one of the most unknown things that we have in logic. It's the relation between these two that says if the zero substitution theta is tau well founded, then we can define it as you can see, and it is going to be faithful with that definition, and it's going to be equivalent with this one. And if the L box substitution is then this time faithful, then we can define theta as follows, and it is going to be how well founded, and this equation is going to be happen. And I wrote what are these gamma theta and theta tau, and it's more the technical things, so I'm going to skip it. But if you have any questions, I can answer it later. And the minimum number in this definition is the minimum number of uh, a minimum number that is going to stop the moving forward. And most of the time, it is the depth of the boxes that is going to appear in the formula. The maximum depth is something that we are going to use as n. And before we address the final result, we need another definition, and it's that tau injectivity. And once again, I want to give you the simplified form of that, and it says that if two different box formulas are mapped to the same parameters, then it is not the case that those are important for our unification process. So we can say that it is not important for our unification type. So if those two boxes are become equivalent in the process of unifying. And the main result here is that for every injective unifier that we have, there is a more general injective unifier which is also faithful. Faithfulness is that we don't have anything outside the subformula. Injectivity says that if two box formulas come to same parameter, then it is not important for us. It's okay. It doesn't have the power over the unification process, and the lemma says that for every injective unifier, there is one which is also injective and also faithful. And the injective unification type of CL box, this time the result is for the CL box plus, is finitary and Fragile. That probability means that almost the faithfulness for the meaning that I had in mind from the beginning, that it is not outside the formula, it's something inside the subformula, inside the formula itself. And to address the main actual result is that we at the beginning, from the beginning, we're looking for the unification type of CL box clause, and we now can say it is finitary. As this is the definition of faithfulness, something we had in mind, and then for A in L box, we can do the proof by induction on the depth of A, and by box steps, as I said, we mean that the boxes that appear in the formula, the depth of boxes that appear in the formula, that's something we have in mind. And we know that by induction hypothesis, we assume that we know the formulas which have less depth than A or have a complete set of unifiers which we call sigma B. And then for the A, we create this set, which is the set of all outer box subformulas that appear in A. And then we partition this set and call it P as the partition of all the things that we have in B. And then for each partition, what we are going to do, what does this mean, is that we are going to, for each partition, and we are going to equivalent the members in each set of that partition. That's something we had in mind. And since we do all the partitions with all the things that are appear in them, so we know that we have so many bx like this, and then we can compute its since it has the less step than the A at the first, we can compute its complete set of unifiers, and then for every partition we are going to union them and create the big lambda A. And finally, we are going to calculate the sigma, which is a combination of these two, and lambda is as before, and theta is the set of injective unifiers of lambda A that we see before. It is finitary, so we have this finitariness and this, and then we combine it. They are also going to be finitary. And as a future works that we have in mind is that what is the unification type of CL box? CL box plus has the weakness extension, but actually we started with also the CL box at the beginning without the necessitation that rule that we have, and it is also interesting question to answer, because there we don't have the necessitation, the equivalency between formulas gives the box formula, equivalency of box formula. And one of the questions is that what is the unification type of CL box only? And another question is that what is the unification type of restricted unifiers in intuitionistic logic? We have the result for classical logic, but something also we are looking for is the result on the intuitionistic logic, the restricted F function types. And also we can say what are the admissible rules of CL box clause, or even if we have the unification type of CL box, then we can also do the same thing, admissible rules of CL box itself. And thank you for your attention, and I'm ready to answer your questions. Actually, I can go back to the, yes, starting from here, maybe you have some questions.
Okay, so maybe you can comment. So what is exactly the difficulty of kind of kind of classifying admissible rules of CL box plus?
Most as I see in the papers, when they compute the unification part, they're also characterizing it might be difficult because the characterizing of the admissible rules because there also you have to say that the admissible rules are this and this, only this. That's
Yes, so it's just some amount of additional work.
yeah, it can be some sort of additional works. Yeah, it needs something to characterize it and to define that it is the only thing that we have, and there is no more admissible rules that we miss. These two can be difficult, but we haven't.
So, but usually, what is approach? Usually, you first classify unification type. And then the next step, and then you have extra step of
Yeah.
you kind of using already knowing how like unifiers are constructed in order to
Compute the admissible rules. Yeah.
yeah, I guess usually
Yeah.
people want to like produce like a basis of missing rules or something.
Yeah, exactly. Basis of the admissible rules. Yeah.
Okay.
Yeah.
Well, can I add some comments maybe on the question by Fedor? If I understood correctly, I would say, for instance, in the intuitionistic logic, we had the classification of the unification type for intuitionistic logic by the works of Gilardi. And then afterwards, Rosalie Imhoff characterized the admissible rules by providing a base for all the admissible rules. So
Okay.
the question probably could be the equivalent work for this CLB plus. So finding a base for the all admissible rules.
Any other questions?
Okay.
Okay, yeah, then let's send things.
Good.